polynomials and things get large, and you have to repeat this for a lot of values. Like here, this was an iterative algorithm where we keep incrementing d and checking. But within this algorithm, we also end up having to do some iteration over e, and then there are some details that I didn't mention about how you check when e is good enough, and that's also expensive. And then the deflation ideal also ends up being quite a lot of variables. Yeah, basically, you end up with a lot of really high dimensional things, and there's a lot of iteration.
But you sort of go until some criteria. Well, you do go until something is satisfied, but it doesn't mean that you're checking everything that must have been checked. So it's why.
It's not a complete algorithm, you know.
Well, there's no guarantee. That's what numerical things are anyway.
Well,
So
it's not true. I mean, things can.
oh yeah, they could get.
No, my question was actually the opposite. So since you're not using any bounds, you're just checking until some conditions.
So you're saying just try it with a high value and see if it works?
No. Well, that's maybe an alternative, but I don't know how it's much more.
There's no way to know that it stops.
No, yeah, but my question is why will symbolic algorithm be faster when here you check everything that you must actually check. You stop.
I see.
So the symbolic algorithm doesn't generate high degree more variables, or
yeah, that's true. Yeah.
Is that the main difference?
The symbolic algorithm is also pretty tedious. I mean, if you look at Barry traders, I mean that's the starting anyway. It's an induction of dimension.
Yeah.
Back to zero dimension.
Yeah, it is.
Very expensive.
It is true. The symbolic algorithm is also expensive. Yeah, I mean, I guess.
The symbolic algorithm is supposed to do factorization, isn't it?
Oh no, that you can avoid.
To compute prime components? Are you joking?
I think there are square-free factorization kind of thing that you could help.
Yes, but not to compute the prime decomposition. Or primary decomposition.
I'm not sure about that actually.
So when, at the beginning when you mentioned Grobner basis for symbolic algorithms, how can you use just Grobner basis?
You mean for primary decomposition?
Yes.
Oh, yeah. I mean, you can't just use Grobner basis, but it involves.
So
Barry trader.
Yeah, Barry trader algorithm.
Does that go through Grobner basis?
It probably,
Yeah.
it probably has improved sometimes by now. It's 1980 something.
Yeah, some Japanese have done something, I think.
So,
I mean, I guess I don't have. I guess maybe the best answer I can give is we've run this on small examples and it's quite slow.
And you compare it and symbolic was faster. So you have concrete examples when symbolic was faster.
Yeah. I mean, it's slow even on very small. Like this will take maybe a minute or two on small examples. So that's not good, right? I mean, it's probably going to be made better. Ours is obviously not optimized to the degree that off the shelf symbolic algorithm is, but yeah, I don't know the version that we have. It's.
Mm-hmm.
So if you're not interested in the multiplicity primary decomposition, and you just look at the numerical prime decomposition algorithm, how does that go? Is that expensive?
Yeah, I don't know how to find the primes to sort of do a process like this. I don't know of a way to make this faster.
So you go through primary first and then the prime.
Yeah, so when you do a primary decomposition algorithm, I mean the question is, what do we count as an acceptable output for a numerical version? And here it's going to be witness points on each component, and then if you want to know multiplicity structure, you can compute dual space information and say things about it. And if you don't want multiplicity information, then don't do that, I guess. But I don't know of a shortcut if you don't if you only want the primes, I don't know a way to do it faster.
More questions? Comments? Okay, thank you very much.